So today we'll be starting reinforcement learning. I helpfully put in a big in buzzword because that's one of the buzzwords that probably many of you have heard thanks to AlphaGo. So this is the buzzword part of the course that will start now. Before I go forward, are there any questions about anything else? Okay, so the best way to think about, so basically the word learning is coming for the first time in the class today, okay? And interestingly, actually we will still be in atomic models. Atomic models essentially means that the states are black boxes, and when you do an action, you get to another state. After a set of states, we get probability distributions and so on. There is no internal structure for the states, there are no state variables, nothing yet. Okay, it's kind of quite interesting to have that in the back of your head because actually no other kind of learning is possible in atomic models. Normally, to do learning, we talk about this notion of generalization, which starts with problems that the models that are above atomic, so factored, feature-based, relational, and so on. Okay. Here, it's not at all obvious how to generalize anything, but instead, what you're learning here is essentially the parameters of the Markov decision process. Okay, so in fact, it's worthwhile thinking that we went from A star search to min-max to MDP. In all these cases, you're being told what the quote-unquote the model is. Okay, so in the case of A star search, what is the model? The model is the child generator function and the costs of all the actions that are leading to those children. If you have that model, then the only thing that is left is what's called inference, which is given this model, what's the best, what's the optimal solution. Okay, imagine I'm asking you to solve an A star search problem. And I do not either, first of all, I might give you a child generator, but I won't tell you the cost. Okay, but then I will tell you that when you get to the optimal, when you get to the goal in the optimal path, you'll get a candy. Do you understand what I'm saying? Can you learn essentially what was given to you before for free, which is basically a child generator function plus costs of the actions? Because if I give you the cost of the actions, then it's just normal A star search. In the case of A star search, actually, you know that if you do an action, it takes you to, there are deterministic actions, they take you to a specific state. Okay, so in fact, one of the other things is I may not also tell you when you do an action which states it takes you to. So you know the names of the actions, you try them out and see where you are going, and you keep doing it until you reach a stage where you say, hey, you reach goal. At that point, if you get a candy, how big the candy is, based on that, you know whether or not you have done something right. Based on this, after playing this game enough number of times, could you have essentially got the model that you had as the input before? Do you see what I'm saying? We could do this in the case of A star search. We could do the same kind of an idea in the case of min-max. We just choose to do it in the case of MDPs. Because in some sense, MDPs are more general than all of these. So if you understand, in the case of MDPs, I will give you an MDP. I won't tell you what the transition function is. So I just probably tell you, in fact, in most cases, we'll tell you the action names. In real world, actually, you don't even know what actions are. Okay, but imagine I give you the action names, but you don't know what happens when you do those actions. Okay? And so when you do the action, essentially something will happen, you will find yourself in a new state, and based on that you realize, oh, that means if I do this action, I get to this state. Now, because if this was A star search, you did this action in S1 and you got to S2, you can always remember that action A will always take me from S1 to S2. If it is MDPs, you can't do that because these actions can be stochastic. So this one time it took you to S2. You do it again, it takes you to S3. Do it again, it takes you to S1. Do it again, and so on and so forth. And then after doing the action infinitely often, okay, then you can take the ratio of the number of times you visited a particular state divided by the total number of times you did this action. If you did this, you got the transition probability that this action from this state will take you to this other state. Okay, so I gave you, basically I'm telling you that you have an MDP, but I tell you I won't give you the transition function. I also won't give you the reward function. Except that if you are in the state and the state has a reward, the reward washes over you, so you feel it. You understand what I'm saying? So in fact, when think of yourself as a little kid. You came into this world. In fact, you don't even know what your actions are. All you have are a bunch of effectors. Okay, I have a hand, I have a mouth. In the beginning, everything looks like put it in your mouth and see. Or hit it on the thing and see. Some of those actions we still do. They're very useful actions. Hitting something that's not working is always a good idea. If your computer is not working, hit it once. It works. Right? Some others, like putting everything in the mouth, we stopped doing of late. Okay? But it was like a very popular action when we were kids. And then also if something is bright, you try to kind of go towards it. Okay? And then there are specific sensations you get. You get the sensation of being cold, sensation of being warm, sensations of being happy. These are biologically wired sensations. Like for example, if you wound up putting something in your mouth and it was sugar, essentially it's like taking drug. For a kid who basically was brought up on mother's milk, you guys probably don't remember this, but it turns out that the human milk is not sweet. Okay? And so kids who are brought up on mother's milk, the first time they touch pure sweet, they essentially think, oh my God, you've been keeping this away from me. This is the world I'm in, and I'm stuck with this stuff with no sugary content. Okay? So essentially, they didn't know what sugar was, but we are basically wired evolutionarily to get a high if we basically have sugar on our tongue. So when they eat the sugary thing, they get the reward, and the reward just washes over it. If in fact you are one of those kids who does not have that sensation, that means your tongue doesn't work, then you have to be told, hey, you ate this candy, you're feeling sugary sensation. And that's no fun. Right? Because that's like you're saying, you should enjoy this class. I'm telling you this. That's no reward. You should just enjoy it by, the enjoyment washing over you. That's reward. Okay? Again, think about this. Actually, these things, for example, when the kid actually kind of walks over a sharp object, they will feel pain. That's the reward that washes over them. Imagine kids who don't have proper sensation in their feet. In fact, older diabetics don't have sensation in their feet and in their extremities. And many diabetics wind up dying of gangrene. Gangrene has nothing to do with diabetes. Gangrene is basically what happens when you got hurt and there's a wound, and the wound sepsis sets in. Normally, as soon as we basically have a wound, we know because we have the pain sensation. The reward just washes over us. The negative reward washes over us. When we don't feel the pain sensation, we don't notice it. And then that can lead to gangrene, that can lead to sepsis, that can lead to all sorts of crazy things. The point I'm trying to make is you are not given either reward or the transition function. But if you are acting in the world, you will feel the reward in the state. Okay? And being depressed to some extent is not feeling rewards in states. Right? I mean, there's nothing happened to me. Even though I gave you a candy, or even though you said, you just won $10 million, and if you don't feel any happiness, then that's because essentially your pleasure centers have been compromised. And then, of course, that leads to its own problems. So we'll just assume that the reward can be sensed when it is offered to you. We can assume still that this is MDP, so if you are in a particular state, you know what that state is. So my question then is, can I solve this MDP optimally? That's what I want to know. Okay? Remember that if I am given T and R, we spent all the last 3 classes almost trying to figure out how to do value iteration, how to do policy iteration to compute the optimal policy. And the class before that, which is the end of the game trees, we talked about how to do online search to compute the policy as needed at the place where you are in. All of this assume that you have the model. The 2 models that MDPs require are T and R. T is a transition function, R is a reward function. Now this is not just MDP thing, it's also A star thing. For A star, the transition function is, if I do this action from this state, where will I go? The reward is the cost of the action. You see what I'm saying? So my question is, if I have a problem solving setup, and I can try it out, I can try this problem out in the real world, can I slowly learn the model so that I can become optimal in choosing my actions over a period of time? And the fact that you are here essentially means probably that's sort of true. Although we tend to think we are doing things optimally, obviously we are not. But at least we can do better than the very first time you experimented with the world. Okay, so this is basically called reinforcement learning. Actually, the word, as I mentioned, the word reinforcement learning comes from psychology literature. This is the Pavlov of our attendance code. And Pavlov basically would do these Pavlovian dog experiments. And of course, that's the joke, that the dog is actually thinking that it's controlling Pavlov, and Pavlov is thinking that he's controlling the dog. But essentially, you're trying to give reinforcements like positive rewards for the dog when it does the right kind of behavior. This is the whole dog training. You still do the same thing. The problem with dogs, unlike humans, is they have no books. If one full generation of dogs learned something, then a new generation of dogs have to learn it from scratch again. Unless at an evolutionary scale their genome changed, there is no way of dogs' kids to capitalize on their parents and their grandparents. We have this nice way of writing stuff down so that previous people, whatever they learned, we just take it for granted. We start from there. We don't have to redo those things. So even now, Pavlov is gone. Before Pavlov as well as after Pavlov, training dogs hasn't improved. It's still the same. Okay? You give them reinforcements and then try to get them to do stuff. And it's very painful. How many of you have dogs, are trained dogs? Yeah, it's pretty painful. Like many people think endearingly that mine is a dumb dog. As if there are some genius dogs walking around. They're all dumb compared to us at any rate. Okay? And I mean it in a non-arrogant sense. Just because we are humans, we have a whole bunch of additional capabilities, and if we are at the same level as dogs, that's basically losing very badly for us. Okay? Anyway, so reinforcement learning is what we're going to be looking at. So as I said, we still have an MDP, and as I said, when I said MDP, it could be A-star search, it could be min-max. You should think of all of them too. I mean, just to be specific, I'll think in terms of MDPs. Of course, which has a set of states, a set of actions, a transition model, and a reward function. This is what an MDP is. If I ever give you this, You can use the value iteration or policy iteration or RTDP. Remember RTDP? The online decision making for MDPs. Any of those algorithms to figure out what's the optimal decision to make or better decision to make. My question is, I don't give you any of this. Essentially, I put you in a state, you know where you are. You have eyes, so you know which state you are in currently. Okay? And then I will say, you're not given either T or R. Can you learn something about this MDP, especially the T and R functions, such that once you do it, you can then do policy and value iteration? Okay? That's reinforcement learning. And again, I keep repeating that this could have been thought of in terms of A-star search too, or in terms of min-max too. Essentially, you're trying to learn the model rather than just do the search. Okay? Learning the model in this context, things is in terms of this is TSAS dash, which will be CSA in the case of A-star search. And then, TSAS dash is children generator function. For A-star search. And then RSAS dash is the cost for A-star search. I'm pushing this because I want you to understand that it's like, again, I want you to stop saying, I'm doing reinforcement learning over MDPs with deterministic actions and a single goal. That means you're doing reinforcement learning for A-star search. And in fact, if you ever find an algorithm for one of these, there should be an equivalent algorithm for something else too. Like for example, I mentioned RTDP in the class. In the slides, there is a version called RTA star, which is the version of RTDP which just does no expectation, just max. Because if you're doing A-star search, it's just, you do an action, you get a single state, single child state. Okay? And basically the ideas of RTA star are connected to ideas of RTDP. It's the same, they're all well-connected ideas. The big difference is, in the case of learning, you're trying to learn these models. Okay? Now, of course, as I said, psychologists have always studied this, and they try to figure out that animals try to learn in terms of rewards. There are all sorts of interesting things. For example, bees learn near optimal foraging plan in a field of artificial flowers with controlled nectar supplies. They just figure this out. They go into a new field, and they still figure out which is the best way to, how much time to spend on which flower. Okay, so bee-brained is not as bad. Essentially, it's learning something. And then, of course, here, these bees have a direct neural connection from nectar intake measurements to motor planning area. So you do the thing that gives you more reward. You see what I'm saying? And the reward has to be biologically built in for bees at any rate. It's not enough for bees to be told in a way. Notice that in the library there is this book in the catalog which says bees are supposed to have fun when having some nectar. Those kinds of bees die because A, they can't read, and then of course B, also they are not finding any happiness in life. They are the depressed bees. Okay? Okay. So animal learning is like this. The real question, of course, is in the beginnings of psychology, one of the biggest questions is how different is human learning from this kind of animal learning? And in addition to Pavlov, there is this other guy called Skinner, B.F. Skinner, whose name I mentioned. And he was into behaviorism. And basically, he essentially said, human intelligence can also be understood just by looking at their behaviors. And also by setting rewards and so on and so forth. To some extent, we do reinforcement learning, but we also tend to have a lot more stuff. Obviously, we also have knowledge about the world, a lot more knowledge about the world that either has been built in or we can read, even if we haven't actually experienced. You understand what I'm saying? That makes a huge, big difference. You don't have to try everything to understand that it's either good or bad for you. You could actually learn from other people's experience. And all those things wind up making a big difference for humans. But people did think in terms of using reinforcement learning in the case of in understanding humans. In AI, reinforcement learning, of course, was oftentimes used in the context of games. And this is not surprising because, after all, the most reinforcement learning algorithms work even now for games, right? I mean, all of you know that this stuff about AlphaGo, Dota, whatever, etc. Why is that? It turns out that if you're trying to learn the world by behaving in that world, you can die. Imagine trying to learn how to climb Everest by just going after Everest. No reading books, no Sherpas, just go and try it out. And you die, and hopefully the guy behind you can take notes. So you don't do what that stupid guy did. And the second guy can do slightly better. Do you understand what I'm saying? But unfortunately, we, as much as patriotism, all that stuff is talked about, we like our life. We don't want to die so that other people can learn because of our death. Okay? So in general, trying to learn by doing is the last resort. If we are learning everything actually by doing, we won't be where we are civilizationally. Okay? There are cases where doing doesn't kill you. Where, for example, doing is playing a game. Right? Playing a game, you lose, you win, you don't die. Do you see what I'm saying? And so there, reinforcement learning is a great thing. Especially if it's a computer game, it's even greater because there is a simulator for the game. And you can try out all sorts of strategies many times. Okay? And there is, in fact, we'll talk about this again, but this issue of the biggest problem with reinforcement learning is actually having to act in the world. And you want to learn as much as possible from very few times you act in the world. Because if you act too long, then you can die. Plus also it's very wasteful. Okay? So keep that in mind. But anyway, so one of the first success stories is Backgammon, which essentially by Tesaro, J.B. Tesaro, who's still alive, who's actually a AAI fellow, and he's at IBM, and he basically did this reinforcement learning based approach, essentially, for learning to play backgammon. Okay, to some extent it's a game. Games have opponents. It's not a pure MDP. But as I said, they're all connected. A-star search, min-max, MDP, they're all connected. So it's not too surprising that you should be able to use reinforcement learning technique for games. Although we won't go into it right away. Okay, so backgammon, he called it TD gammon. And TD stands for temporal difference. We will talk about what that is a little later. And basically he was able to show that it's a world-class player very fast. This was 25, 30 years back already. And again, it does actually, a lot of it does self-learning through simulator. Left to itself, it plays. So you could do self-learning of climbing by trying to climb the Everest. But oftentimes, most people will just die after the first few times. And then whatever they learn just goes with them. But if you have a simulator for going up the Everest, many of you probably tried to play Grand Theft Auto kinds of games and thought that's the way to learn driving, which is part of the reason we have so many accidents. People think, if you die, then you'll get up again. Unfortunately, it doesn't happen outside of Grand Theft Auto. Okay? But essentially, if you have a simulator, then one of the greatest things in simulator is, remember this word we talked about Ergodic? Normal worlds are not ergodic. You can die. That means you may reach a state from which there is no return, which is normally called death. Okay? But in a simulator, when that happens, you restart the simulator. In real life, you can't. Okay? Having simulators essentially allows speeding up trial and error methods. Now, when we think about simulators, for things like computer games, they are computer games. They are their own simulators. From the day one, they were simulators. Most real-world things don't have simulators. To get a simulator, you have to spend tons of money to construct a simulator. Okay? The very first flight simulators were very costly to build. Because basically they will essentially get you into this thing which will also have the exact kind of motions, etc., so that you will feel what happens with the G's and everything. And then you try to figure out how to fly the plane. And still it won't be completely accurate. NASA has huge wind tunnels. How many of you have seen big wind tunnels? NASA has some of the biggest wind tunnels. Wind tunnels are to simulate what happens to things like rockets when they try to fly in the wind. You can have some number of equations, etc., but really the models are not good enough that the simulator is the best way to try. And building one of those simulators is extremely costly. Computer simulators, on the other hand, they're there already, so you just wind up using them. Keep that in mind, that the general problem with reinforcement learning is that when you try to act in the world, that can be very costly. You might learn, but you might learn after a large number of wounds and maybe death. Okay, but if you have a simulator, you can avoid some of that. If it's a computer simulator, you can avoid a whole lot of it. So somebody, for example, put this nonsense, something about these OpenAI stick figures, don't get me started on them, try to learn hide and seek. Really? I mean, it's interesting in as much as, how many of you know the game of life? Okay, stick figures learning cooperation in RL is as interesting as game of life getting into interesting configurations after a while. It's kind of interesting, but what's the application of it? What do you do in real world with that kind of, if only you have 10 billion or 10 trillion, I think in this particular case 500 million iterations were needed for them to figure out a few of the strategies. Okay, that actually shows you how costly it is to learn with, just by acting in the world. And this was a world where A, they don't have any life, and B, they don't die. If they die, they restart again. You don't have that advantage. Okay? If you die, we write in a book saying this is the stuff that happened to him or her, and then we try to avoid it maybe. That's about it. Okay? So keep that in mind. So anyway, in the case of in reinforcement learning, remember the problem itself is trying to learn T and R. Okay? And the things that we try to do is objectives of reinforcement learning are given your effectors and perceptors, and the world, the most general case, the world in the raw tooth and claw. Basically, you're actually working in the world. If you are working in a simulator, it's like a made-up world. That's nice. Okay? And then sometimes a simulator, so you get ergodicity and can repeat episodes. If you have that, then you basically are using that to learn to perform well by doing the right decisions at the right states. And you know that if I'm giving you T and R, you can figure out what are the optimal decisions. That's what the last 2.5 classes were. Now you're trying to learn T and R, and the simplest way to think about it is you learn first T and R, and then learn how to perform that. But one trick that we'll find out is actually, if all you want to do is to learn to perform well, you may not necessarily need to know T and R. You can just directly learn the action. That's something that we can do, and we will see that happening here. So this basically, the way you can do this might involve the most obvious case, which is learn the MDP model. you learn T and R directly. And once you learn the T and R, then, so learning the transition model, learning the rewards, and once you learn them, and the rewards basically, whenever you go into that state, you felt a reward, and you write in your little book, saying I felt this reward. Okay, so if you have learned the rewards and transition, then it's solved problem. Right, because once I know T and R, it's solved. So I reduced it to a problem already solved. You understand that? By the way, so there is this is kind of thing that we do in our subjects, right? We basically go to a new problem and do something so that it gets reduced to an old problem. So if you learn T and R, then this becomes reduced to MDP solving, which we already done. Okay? So that's the most obvious thing, and we will look at this. But there is also other way, which is if all you're trying to do is to figure out what is the optimal action to do, then you can just either learn directly the state value, just learn which states are good, which states are bad. Okay? And you can learn the state value either by learning the V of S or by learning Q of SA. Remember the Q iteration that I talked about in the class? If you do learn Q of SA, let's say, if you learned Q of SA for all actions A and all states S, then I would argue that you know what to do in any state. In any given state, you pick the action A, pick the action A that makes Q of SA the highest for that state. Suppose that state has actions A1 to A4, then the Q values of A1 to A4, you take the max of it. And whichever is that, that's the action you do. It's just one single max. No thinking, just maxing. Okay? So I could directly learn that, and that's basically the idea of Q learning. This is the idea of Q learning. And a connected idea basically called TD learning, we'll look at and talk about it. In both these cases, you never actually take the intermediate step. You don't get the T and R. You just go directly to the answer. It is actually possible. In some cases, that's pretty much the right thing to do. Okay? And then the final thing, of course, is you can try to search in the space of policies themselves and pick the best policy. And this is not policy iteration. This is kind of starting with a policy and greedily improving it. And this is basically, we won't talk much about it, but this is also a very useful technique. It's called policy gradient search. And typically, in fact, it only makes sense in the cases where the policy is represented in a non-atomic or factored form, or feature-based representation of policy, because that's how you can generalize, tweak the policy.